Hello, I am Teacher Melai, and let's talk about operations on sets. So what are the operations on sets? So just like in algebra, so we have operations that can be used in sets. We can also use operations on operations. So we have the following: so union and intersection, complement of sets, set theoretic difference, different symmetric difference of A and B, ordered pairs, and the Cartesian product. Okay, so in the understanding this, we are going to define first the terminologies like union and intersection. So that's for our first operation. So for definition number 1, we have the definition of intersection. And for definition number 2, we have here the definition of our union. So if we so as mentioned, we are talking about sets. So if we let A and B be sets, so we define a set form from A and B called intersection of A and B. So it is denoted by this symbol. So let us consider that. So it's denoted by this symbol, and it is read as A intersection B. So by the rule, A intersection B is equal to X, where X is element of A and B is also element of B. While for our definition number 2, so we have let A and B be sets. We define the union of A and B denoted by this symbol. So it is read as A union B, and this is equal to X, where X is element of A or X is element of B. Okay. So let us move to our next slide. So for example, so if we let A be equal to 2, 4, 6, 7, 9, and B be equal to 2, 4, 7, 10, 16, and C be equal to -2, -1, 1, 3, 5. So our objective is to calculate A union B, A intersection B, A union C, A intersection B, and A union the intersection of C and B. Okay, so what our objective is to answer this example. So let us use the whiteboard. And open Paint for us to answer this. Okay, so going back to our example here, let us consider the example here. So let us answer the item. So what is A union B? So A union B is equal to, so if we will look at the value 2, 4, 6, 7, 9. So for union, we are going to combine elements of A and elements of B. So we are going to simply copy 2, 4, so we have 6, we have 7, 9, 10, and 16. So this is our A union B. So how about A intersection B? So for A intersection B, so this contains the elements in A that is also in B. So what is the common elements in A and B? So we have 2, 4. So we do not have 6 on the other side, but we have 7. So it is 2, 4, 7. So that's A intersection B. So how about A union C? So we will just again combine the elements of A and the elements of C. Okay, so we have here -2, -1. We have 1, 2, 3, 4. We have 5, 6, 7, and the last one is 9. So that's the A union C. So let us also consider A intersection. Oops, we're done with A intersection B. So let us not consider that anymore. So what we need to answer is A union the intersection of C and B. So let us first answer C intersection B. So what is common in C? Elements of C that is also in B. So let's take a look at the values. So we have -2, -1. There's no 1, there's no 3, there's no 5. So this is actually empty or null, or it can be written as like this. So if we have letter A, so the union of A union this element or the elements of C intersection B. So it's equal to, so what's the value of A union intersection of C and B? This is just combining. So we have MP 2, 4, 6, 7, 9. Or we can just simply write this as 2, 4, 6, 7, 9. Or similarly, this is just equal to A. So it is understood that all of the elements here contains also the empty element or empty set. So we can simply write it this way, the first one with the empty number or empty symbol, or we can just simply write it as 2, 4, 6, 7, 9, or it is equal to A. So A union, the intersection of C and B is equal to A. So that's how to solve for union and intersection. Okay, so let us also consider, so let's go back to our PowerPoint. Complement, operation complement. So what is complement? So complement by definition is if we let A be a subset of a universal set U, so we define the complement of A. So it is denoted by A with apostrophe. So by the rule, it means that A complement is equal to X element of U, where X is not element of A. Or in other words, this can be stated that the elements of A complements means elements of U universal set not in A. Okay, so let us consider an example. So if we let U be a set of real numbers, so if we let U be equal to R, or U is elements of R, so we solve the complement of, let us solve for the complement of the following. So how will we deal with this? So again, we need to open our board. Okay, so let's solve this. So A prime is equal to, so we are not going to include negative 2. So it will be from negative 2, negative infinity. So negative infinity to negative 2 union on the other side of our number line, just in case we use number line. So since 2 is included in the set, so I'll use open parentheses or the round parentheses 2 to positive infinity. So this is a complement. How about for B complement? For B complement or complement of B, so we have here the values. So we use the interval notation is from negative 5 to 2, or it means that x is greater than negative 5 but less than or equal to 2. So what are the values now of our universal set? That is not the value of B, or not contained in the value of our set B. So which means, so we have open bracket or open round bracket. So we are going to use negative 5 with square bracket until negative infinity union. It is a square bracket, so I'll use around 2 to positive infinity. So this is B complement. So let us also consider the C complements. Elements of U not in C is equal to, so we are not going to include 1 to negative infinity. Instead, we are going to consider less than, or rather, what do you call this? So can we do that? So excluding 1, so we can use again open, round bracket to positive infinity. And for D, so it is from 1 to positive. So we are going to consider the other side. So it's from negative infinity and 1 is included. Because in the D, 1 is not included because it is in interval notation and the symbol used is the round open parenthesis. So this is the answer for our example. So we have the following. So negative negative infinity to negative 2, union 2 to positive infinity. So negative 5 to negative infinity, union 2 to positive infinity, and 1 to positive infinity, and then 1 to negative infinity. Okay, let's again go back to our presentation. How about set theoretic difference? So for set theoretic difference, so we have the definition that if we let A and B be set, so we define the difference B and A, which means as B minus A, or by the rule, B minus A is equal to X, where X is element of B and X is not an element of A. Or in other words, elements in B, not in A. Okay, so we have here an example. So how will we show now that elements of A? So we have the following we have the following values of or elements of rather set A. So in doing this, again, we are going to change our screen to with our board. Okay. So going back here, as mentioned, A minus B is elements of A not in the B. So let us look at the elements of A. It is 2, 4, 6, 8, 10, and elements of B, 1, 2, 3, 4, 5, 6. So what are the elements of B that can be seen in A? So we have the elements 3, it's 2, 4, and 6. So A minus B is equal to what are the elements not in the B. So we have the common is 2, 4, and 6. So we have 8 and 10. So elements in A that is not in B is 8 and 10. How about B minus A or elements in B not in the A? So as mentioned, the values that is common is 2, 4, 6. So that means that the elements in B not in A are 1, 3, 1, 3, 5. So we have B minus A. So let us move to our next slide. So how about symmetric definition of A and B? So for the symmetric definition of A and B, it is denoted by A symmetric difference. It is symmetric difference of A and B. So it's A triangle B. So by the rule, it means that it is the union of A minus B and B minus A, or A minus B union B minus A. And we are actually done placing A minus B or computing for A minus B and B minus A. So to compute for the A triangle B, or as mentioned, symmetric difference of A and B, this is the intersection of 8 set with 8, 10, and 1, 3, 5, which is equal to 1, 3, 5, 8, 10. So this is the symmetric difference of A and B. Okay, so let us also consider definition number 6. So what is ordered pairs and the Cartesian product? So given the ordered pairs AB and CD, we say that these ordered pairs are equal. So it is denoted by, so we have ordered pair AB is equal to CD if and only if A is equal to C and B is equal to T. Okay, so let's go back. So how to show this? So for example, so we have set A with elements or in interval notation, or rather, we have the following set. So is what they think is so we say that it is equal if, for example, we have set A equal, for instance, to 2, 3, 4, and set B. So we can just disarrange this 3, 2, 3, 2, and 4. So we say that these sets are equal since it contains 2, 3, 4, and 3, 2, 4. So using this definition now that the given pairs A, B, and C, D, these ordered pairs are equal if AB is equal to CD, if and only if A is equal to C and B is equal to D. So which means, for example, if we have 2, 3, and 3, 2, we say that this is equal because even if we interchange, as mentioned before, even if we interchange the values, it is still equal. But what if, this is for set, but what if we have notation, let's go back, let's say from 1 to 2, and the other one is 2 to 1. So for this ordered pair, so can we say that ordered pair 1, 2 is similar to, or rather equal to ordered pair to 1? So based from the definition, of course, the value of A here is 1 and the value of B is 2. So the value of C here is 2 and the value of D is equal to 1. So which means 1, 2 is not equal to 1. So that is how ordered pairs and ordered pairs can be related here. But for, as mentioned, for sets, even if we interchange the value, we can still say that it is equal. Okay, going to the next definition. Given sets A and B, so we define the Cartesian product AB. It is read as A cross B Cartesian, and it is often called cross product. So by the rule, A cross B is equal to ordered pair AB, where A is element of A and B is element of B. So let's say, for example, set A contains 1, 2, 3. And set B contains, let's use letter X, Y, and Z. So A cross B contains the ordered pair 1X, 1X, 1Y, 1Z. So it can also contain now 2X, 2 ordered pair to Y, ordered pair to Z, and also 3X, ordered pair 3Y, and ordered pair 3Z. As mentioned, A is element of our set A and B is element of our set B, which is, of course, the case in this example. Okay, so our reference material is Morash, the book of Morash entitled Bridge to Abstract Mathematics. So thank you for watching.